In this problem, we're told that 13.8 liters of ethylene gas, C2H4, at 21 degrees Celsius and 1.038 atm burns completely with the oxygen in the air. The resulting CO2 is collected at 44 degrees Celsius and 0.989 atm. How many liters of CO2 is collected? We begin as we would with any stoichiometry problem by writing the balanced chemical equation and organizing what is given in the problem. We are told the starting volume of ethylene gas. However, that gas is not at STP, and we are asked to find the final volume of CO2 produced. However, once again, that gas is also not at STP. Also, since the problem states that the ethylene burns completely with oxygen in the air, we don't have to worry about a limiting or excess reactant in this problem. However, as you can see, our temperatures were given to us in Celsius, and that can't be if we're going to use the ideal gas law equation. So we have to convert those to Kelvin by adding 273 to each of them. So now as we look at a solution map for this problem, the first thing we have to do is take our given amount of substance A, in this case the 13.8 liters of ethylene gas, and convert that into moles of substance A. To do this, we're going to use the ideal gas equation arranged to solve for moles N. Next, what we'll have to do is we'll go from moles of that substance A, the ethylene, into moles of substance B, which is going to be the CO2. Just like any other stoichiometry problem, we're going to use the mole ratio from the balanced chemical equation to help us go from moles of substance A into moles of substance B. And lastly, we're going to go from moles of substance B, which in this case will be CO2, to volume of substance B. And again, because it is not at STP, we're going to use the ideal gas law equation again, but this time it's rearranged to solve for V. Now the work for part 1 of the problem will look like this, where we solve for N, which is moles, by multiplying pressure times volume, so that's 1.038 atmospheres times 13.8 liters, and then we're going to divide that by the product of the ideal gas law times the temperature in Kelvin, so 0.0821 atmosphere liters over mole Kelvin times 294 Kelvin. I want you to notice how the gas constant R in the ideal gas law equation has units that cancel out with all the other units in the equation except for mole, which is why our answer will be in mole. And if we compute that answer, we find it to be 0.593 mole of C2H4. Now that we've found the moles of substance A, which is the ethylene gas C2H4, it's time to go from moles of substance A into moles of substance B, which is going to be the CO2. Now remember, we do this using the mole ratio from the balanced chemical equation. So we start with our moles of A, which is the C2H4, the ethylene. We have 0.593 moles of ethylene, and we multiply that by the mole ratio, which in this case, we have 2 moles of CO2 on the top, 1 mole of C2H4 on the bottom. And remember, we're getting these values in the mole ratio from the balanced chemical equation, the coefficients in front of the 2 chemicals we're discussing. And just like all dimensional analysis, since we have mole of C2H4 on the top, that cancels out with the mole of C2H4 down on the bottom, and that leaves us with our answer of 1.19 mole of CO2. And now that we have moles of CO2, we can find out what we want of CO2, which is the liters of CO2. But since it's not at STP, again, we're not going to be able to use the molar volume. We're going to have to use the ideal gas equation rearranged to solve for volume. Now, how do we get this? Well, if we take our PV equals nRT and we multiply both sides by 1 over P, the pressure units on the left side of the equation cancel out, and that leaves us with this final equation. Now we simply input our values into that equation, where our moles came from the prior step in the problem, and the other values came from what was given originally. Again, noting that the units in all the variables in the equation will cancel out with what units are in the gas law constant, leaving only the unit that we're solving for. And if we compute this, it gives us our final answer, which is 31.3 liters.